pitcher delivers a fastball with a velocity of 43 meters per second to the south. So I'm going to draw a picture. Here's the pitcher's mound. The baseball has a velocity of 43 meters per second to the south. At some point, here's a guy with a baseball bat. At some point when it hits the baseball bat, afterwards it's going to have a velocity of 51 meters per second to the north. And the question says, what is the average acceleration during the 1 millisecond contact time with the bat? Okay, so I can simply list out my kinematic variables. I have xi, x final, v, I'll call it vxi, vx final, a t, I guess we can say ax. So its initial position, no idea. Its final position, no idea. We know its original velocity is 43 meters per second south. I'm going to call north the positive x direction. Oops. So its original velocity then would be negative 43 meters per second, and its final velocity would be positive 51 meters per second. Acceleration, we don't know that. That's what we're looking for. Time is 1.0 milliseconds, or 1.0 times 10 to the negative third seconds. If I look at the kinematic equations, I can say V initial equals V final. I'm sorry, I got that backwards. So if I look at the kinematic equations, I can say V final equals V initial plus acceleration times time. Nothing is zero, so I'll just have to solve for acceleration. So acceleration equals V final minus V initial over time. That is exactly the same as using the definition of average acceleration, which is delta V over delta T. So A then is equal to V final, which is 51 meters per second, minus the negative 43 meters per second that the ball came in with, over the change in time, which is 1.0 times 10 to the negative third seconds. Units, meters per second equals meters per second times 1 over seconds equals meters per second squared. The units work out. So A equals minus minus becomes a plus. (94,000) meters per second squared. Make sure, yep. That's a huge acceleration, of course, because it's a huge force imparted onto the ball.